All right, let's put on our detective hats today. We're going to open up a case file on a function that honestly looks completely innocent, but it's definitely hiding a secret.
So here's the mystery we need to solve. You look at this function, and everything about it says it should graph a perfect, simple, straight line. But if you go and ask your calculator, hey, what's happening exactly at x equals 2, it just gives up. It flashes error. So what's the deal? How can a straight line just, break at one tiny spot?
Okay, so the secret to cracking this thing is all about how we look at it. We're not dealing with some giant, uncrossable wall on the graph. Nope, it's way more subtle than that. The best way to think about it? It's like a single, invisible, missing pixel on a high-definition screen that's otherwise perfect.
So this missing pixel actually has a fancy official name, a removable discontinuity. Yeah, I know, but honestly, I like its nickname way better, a hole. And that word removable is the really important part. It means we can use a bit of algebra to find this hole and kind of patch it up just to see what the graph is supposed to look like there.
So, how in the world do you find something that's invisible? Well, lucky for us, we've got a super reliable two-step method. It's like our standard issue detective kit for these cases. First, we're going to do some factoring and canceling. Then we'll use the clues we find to pinpoint the exact y value of that missing point.
Okay, let's head to our first crime scene. Here it is, the function that started this whole investigation. Y equals x squared minus 4 all over x minus 2. This is the culprit that's giving us that weird error at x equals 2. Time to dust for prints.
First up, step 1, factor and cancel. Let's look at the top part, the numerator. That x squared minus 4 should look familiar. It's a classic difference of squares. It factors out into x minus 2 times x plus 2. And look at that. We've got a matching x minus 2 on the top and the bottom. So we can cancel them right out.
And once we do that canceling, check out what's left. Our function, which looked kind of complicated, has suddenly simplified down to just y equals x plus 2. That's just the equation for a straight line. It's like the part that was causing all the trouble just disappeared. But wait a second, not so fast. We can't just forget about that piece we canceled out. That x minus 2 term, that's our prime suspect. The value of x that would make that term equal to 0, that's our culprit. So you set x minus 2 equal to 0, and what do you get? Bam, x equals 2. We've found the exact x-coordinate of our missing pixel.
Okay, time for the final step in our investigation. We take that x value we just found, x equals 2, and we plug it into the simplified function, y equals x plus 2. And this is super important. It has to be the simplified one. This is what tells us where the hole should be. So we plug it in, y equals 2 plus 2.
And there you have it. The missing pixel has been found. Case closed. The hole is right at the coordinates 2, 4. So this function looks and behaves exactly like the simple line y equals x plus 2, everywhere except for that one single invisible spot. So we're getting pretty good at spotting these holes, but it's really important to remember that not all gaps you see in a graph are these nice, neat, fixable points. Let's take a quick look at another kind of gap so we know how to tell the difference. And the difference is actually pretty simple, but it's absolutely crucial. So you've got holes. Those come from the factors on the bottom that you can cancel out. There are little fixable missing pixels. Then you've got asymptotes. These come from factors on the bottom that you can't cancel. They stick around and create these huge, unfixable, infinite gaps. Remember those walls we talked about? That's them. All right, a quick heads up, a little word of warning from the field. There are a couple of common mistakes that trip a lot of people up. The first one, trying to plug the x value of the hole back into the original function. Don't do it. You'll just get that division by 0 error every single time. And the second one, it's really easy to simplify the function and then totally forget the hole was even there. You've got to remember where it came from.
Okay, so we've done all this detective work. We've found this invisible problem. We figured out how to fix it with algebra. But you're probably sitting there thinking, so what, right? Why does this tiny little algebraic trick actually matter? Why do we care so much about one missing point?
Well, here's the thing. This isn't just some clever party trick with algebra. It's actually a huge stepping stone. Right now in Precalculus, we're learning how to find the hole. That very same skill is what you're going to need to find something called the limit, which is just the value a function is getting closer and closer to. And that leads you straight to the heart of calculus, the derivative, which is all about finding the slope at one single specific point.
See, when you get to calculus, your whole point of view just flips. You're not trying to avoid that undefined point anymore. Actually, that exact same problem point, it becomes the entire focus. The whole goal becomes figuring out exactly what's happening right there at that spot.
And this is the big reveal. The hole that we work so hard to find, it's not the problem anymore. In calculus, the hole is the answer. That's the whole point. It represents something incredible, the instantaneous rate of change. The precise slope of a curve at a single point, something that without this trick would be literally impossible to figure out.
So that missing pixel, that little error your calculator spits out, it's not a mistake you should just ignore. It's a clue. It's really the gateway to understanding one of the biggest, most powerful ideas in all of math, the very nature of change itself. And it all starts right here, with finding that one little hole.